Oh, hello, Science Alliance. Hello, I'm Lara. I'm trained to teach physics to A-level. So this is the bit of my job where I really do what I'm trained to do, I suppose, because it's IGCSE physics. We're on the third lesson of electricity. All the previous lessons are available to watch on my YouTube channel. You're here, you probably know that. I have asked you a question, because we're doing currents today. When you switch on a light switch, the light comes on straight away, yeah? Why is that? What are the electrons doing? So last week we looked at conductors and how metals are good conductors of electricity because they've got their protons, their little positive particles, in a kind of framework, but the electrons are just free. You remember free electrons? It's a natural thing. They're free to move around. They can jump from proton to proton. So this is the first thing that we have to talk about when we talk about electric current, is this big misconception that because you turn on a light switch, the light bulb lights up straight away. Electrons must be speeding from the light switch to the bulb at the speed of light. That is actually not what's happening. I have done can't call it a diagram, a poor picture of a kind of model of an electric current to try and explain to you why this is not the case. I'm sorry it's not a very eco-friendly model, but there you go. We've got a coal mine, right? And some trucks which are carrying coal to a power station and then giving the coal to the power station, and then the trucks are coming back empty, okay? I'm going to keep coming back to this model over the weeks, I think. So the coal mine is the thing that makes the trucks move, right? Without the coal mine, there'd be no coal, there'd be no point in the trucks moving. The trucks move along the road and the power station use up the truck's coal. So why is this a model for an electric circuit? Go on, 5 seconds. What's the coal mine? What are the trucks? And what's the power station? 5, 4. What's an electric circuit? Maybe you don't even know. That would be good while you're here. So the coal mine is the battery, right? It's the whole reason that the trucks are moving around the circuit. So the trucks are the electrons. And the power station is, I've said bulb, etc. So it could be anything, but it's whatever you're trying to make work with your electricity. So can you see, can you see that if all these things were frozen and you suddenly shouted, go, a truck wouldn't go from the coal mine, like, whew, to the power station, but coal would immediately get to the power station because there would be a truck there full of coal, like ready to deliver it. You see what I mean? So as soon as the trucks start moving, coal starts getting to the power station, but no one truck is moving really quickly. Yeah, that's all right. Yeah, you see what I mean? So it is with electricity. When you get to A-level, you learn about something called drift velocity, which is how fast the electrons are going. They're actually going quite slowly. They're just drifting along. So we've looked at, well, I'll call it a battery for now. Got news about that. But we looked at batteries a little bit last week. I'll zoom in here for you. And how they've got a negative side and a positive side. You see? Positive, and they haven't bothered. Oh yeah, there we go. A negative on the other side. So that's all that is happening really when you plug a battery into a circuit. Obviously it could be mains electricity, which we'll talk about later. But you've just got a wire, you put a battery in, and the electrons in the wire are attracted to the positive side, because opposites attract, and they're repelled by the negative side, so that's why they just drift along and deliver energy to the circuit. Okay, I should probably show you a picture of an actual circuit. So there's only 2 things really that you need to make a circuit work, to make electricity current flow through a circuit. You need a source of energy. So like I say, in this case, it's the coal mine. If the coal mine disappeared, regulars know how the coal mine is going to disappear. Can't get over this flame effect. If there's no source of energy, the electrons cannot move, yeah? And similarly, it's got to be a complete circuit. So if there was some kind of terrible earthquake and a crack appeared in the road, these trucks would not be able to move. The whole thing would grind to a halt. It's exactly the same with the current. Let's show you an actual circuit diagram. We've got a bulb, a battery, and a wire. If the battery disappeared, the electrons will not flow. Obviously, they've got no reason to move. But also, if you put a switch in the circuit and you open it, then you're creating a break in the circuit. So again, the electrons can't flow, okay? They've got to go from the battery to the bulb and then back to the battery to gain enough energy to keep working. Yeah? Okay, good. For current to flow, there must be a source of energy and a complete circuit. All right, this is nice. What a lovely, easy thing to tick off for you on your specification, which, you know, is what you need to know for your IGCSE exam. You have to know that lamps and LEDs, just another kind of light, we'll talk about them in a later lesson, can be used to indicate the presence of a current in a circuit. So I get to get my charity shop circuit kit out, right, and show you this. So here is a circuit, batteries, bulb, wires. If I complete the circuit and the bulb lights up, I'm just going to stick this extra little wire in. Is there a current flowing through that circuit? Yes, no, or can't be sure. Is there a current flowing through this circuit? Yes, no, or can't be sure. 5, 4, 3, 2, 1. Yes, there is. There definitely is. There must be a current flowing through the circuit if the bulb is lit up. That's the only way that the bulb could light up, is with a current flowing. If I do this, pretend that this is a completely new circuit. You've got no preconceptions about this circuit. Is there a current flowing through this circuit? So it's exactly the same as before, it's just a sort of loop, but I've put another piece of wire in the centre, kind of cutting off the battery from the bulb. Is there a current flowing through the circuit? Yes, no, or can't be sure. The bulb's not lit up, I should say. Probably, isn't it? Maybe. What could be happening is that current could be flowing from the battery just through the wire and back into the battery again without lighting up the bulb. The bulb could be kind of getting cut off. We'll talk more about that later. But you don't know, do you? Not necessarily. It could be that the batteries are both dead. It could be that the bulb is broken, so that's causing a break in the circuit. So you don't know. So just to emphasise, a bulb not being lit up doesn't necessarily mean that there is no current flowing through the circuit. But a bulb being lit up definitely means that there is. Yeah? It's a nice one to start with, isn't it? There you go. Nice if you got a mark for that. Right, let's talk about circuit symbols so that you can do the little quiz that I've got for you. You've already seen quite a lot of circuit symbols on the board there. A lamp, obviously there's loads for you to learn, but it makes sense that we learn them as we come across the thing. So this is a bulb. If you've got like a really old textbook at home, you might see something else, but this is what you need to learn for IGCSE, just a circle with a cross through it. The switch is always a fun one. It's just a straight line with dots to show a closed switch, and then to show an open switch, you kind of lift one of the dots up and leave a gap like that. So that's written. I can feel people on my Facebook page going, "Lara, stop writing backwards. You're not on Facebook, you don't have to write backwards." Switch. So that would be called a closed switch because it's closed. Current can flow through it, and this is an open switch. Creates a break in the circuit so that current can't flow through it. Right, what else have we got? Oh yeah, so this thing that I've been waving around and happily calling a battery, it's not actually a battery. I'm sorry, it's not me, it's physics. It's actually, one battery is called a cell. So to draw a cell, it's just a long line and a short line kind of breaking across the wire. So the long line is representing the positive end of the battery. Sorry, the cell. And the short line is representing the negative end of the cell. So if you put more than one cell together, doesn't matter how many, you call that a battery. So to draw that, it's just as many cells as you have in a row. So I'll just do two. Long, short lines. That's a battery. Ugh. I don't know. There. I think the only other thing wire, we shouldn't forget about wires. Wires are just straight lines. Yeah. And the only other thing that we've looked at so far briefly, or we will look at in this little quiz, is an ammeter. A circle with an A in it. That's something that you use to measure current. We will talk more about that later. Little notes. When we've been talking about like running 5 meters, we've been spelling it M-E-T-R-E because in British English, meter, like a measurement, is R-E at the end. But if we're talking about our electricity meter or a meter that measures something, we do the American thing. So an ammeter is A, 2 M's, and then E-T-E-R, because it's a meter that is measuring something. I'm not going to get tested on that, but, you know, point it out. Right, you have all the information you need to tell me if these bulbs will light up. Here's your little... Let's call it a quiz. Here we go. Would the bulb light up? So you've got A, B, C, and D. A is a battery and a bulb. joined up with wires. B is basically half of that, so there's no wire going from the bulb to the battery. C is a battery and a bulb and an open switch. And D is a bulb and a closed switch. Which one of those bulbs will light up, please? Say in A, B, C or D, will the bulb light up? Done? Okay. So A, this is a battery and a bulb. Yeah, that's definitely going to light up. B, there is definitely a break in that circuit. The electrons, they're not going to travel from the battery to the bulb and light it up. They need to get back to the battery, so that's definitely not going to light up. C, the switch is open. We've got a break in the circuit, so that's not going to light up. And D, did I manage to catch you out? The switch is closed, but there's no battery, so it's not going to move anywhere. All right, next one. E, F, G, and H. So E is a battery and ammeter to measure current and a bulb. F is a battery, an open switch and a bulb, but I've said if I close the switch, will it light up? You've got to be very careful there. G is a bulb and a closed switch, and H is a battery, a bulb, and just a wire, but a really, really, really wiggly wire. All right, let's have a go. So E, will the bulb still light up with an ammeter in it? Yeah, of course it will. It's the whole point of ammeters. We'll do more about this later when we get to resistance, but an ammeter, I mean, its job is to basically just not affect the current at all, because it's supposed to be measuring current. So it wouldn't work, would it, if it was measuring current and when you stuck it in, it changed the current. So no, having an ammeter in a circuit like that is fine. This one with the open switch, that won't work because the switch is open. If I close it, will the bulb light up? No, because look, what's happening here? Did I manage to catch you out? The battery, instead of being short line, long line, short line, long line, is long line, short line, short line, long line. That is not going to work because just in the same way as when you actually put batteries into something, you've got to have the negative end and the positive end both kind of attached to the circuit at opposite sides, yeah? Because the electrons have got to be repelled by the negative side and attracted to the positive side. If you've got positive on both sides, the electrons are just going to be like, it's not going to push them along, they're not going to know where to go. Or two negatives, yeah? They're just going to be repelled by both sides. That's not going to get them flowing around a circuit. So that one will not work, however hard you close the switch. G, no, because it's got no battery attached. And H, yeah, that's fine. It's just not a very well drawn diagram, but obviously current can flow through wiggly wires. It does all the time. But if you're drawing a circuit diagram, do make sure that you always have straight line wires. Okay, last one. Would the bulb light up? This is for the people who've been getting a bit restless, like, oh, this is too easy. Go on then. I, J, K, and L. And you can tell me what you might see in each case if you like. So I is two bulbs and a battery. J is two bulbs and a battery, but it's what we call a parallel circuit. The wires split and there's a bulb on each bit of wire that is split, and then the wire goes back to the battery. K, you've got a battery and a bulb, but then there's just a sort of bit of wire coming off either side of the bulb leading to an open switch. Is that bulb going to light up? And L is the same as J, it's the parallel circuit with a bulb on each kind of split of wire, but there's an open switch between the battery and the bulb. Are the bulbs going to light up? And what would you see in each case? Let's do it then. Yeah, they would light up. You've got a battery and bulbs, fine. J, they would both light up actually, yes. That would be fine. We will talk more about why later. K, yeah, that bulb would light up because you've got a complete circuit. The electrons can flow from the battery through the bulb and back again. This extra bit of wire on the end of the bulb with an open switch, it just might as well not be there. The electrons, I mean, they don't have brains, but they just know not to flow through that wire because that switch is open. It's dark magic at this level. And L, there's no complete circuit there, is there? There's no way the electrons can flow from the battery to the bulbs. So that one, they definitely would not flow. Right, moving on then, let's get a little bit mathsy. You've got to know that current is the rate of flow of charge. That's what Edexcel says if you're doing their exam. Cambridge, I like how they say it. Current is the charge passing a point per unit time. Current, what current is the charge passing a point per unit time. So we need to talk about charge. What is charge? What is charge? So we've talked a lot about charged particles, right? Protons and electrons. We're doing electricity, so we're mainly going to talk about electrons. Current, by the way, could be a flow of any charged particles. It could be, positively charged particles, but generally it's always metals, so it's always electrons. Well, charge is measured in something called coulombs. I need to do a pen sort, don't I? This is poor pen show. Coulombs is what charge is measured in. And it would be very nice, wouldn't it, if like one electron had 1 coulomb of charge. That is not the case. 1 coulomb of charge is actually massive. Electrons have a teeny tiny proportion of a coulomb of charge. So don't fall into the trap of thinking like every time 1 electron goes past a certain point in the circuit that's 1 coulomb. But yeah, current is the amount of charge passing a point per unit time. So it's the amount of coulombs passing a point per unit time. I mean, we keep saying per unit time. The classic unit of time that we use in physics is the seconds. So you could say it's the amount of coulombs passing a certain point in the circuit per second. So to go back to our little model, here we go. How would you, in this model then, if the trucks are electrons and the battery is represented by a coal mine and the bulb is a power station, how would you represent an ammeter? So ammeter measures current, and current is the amount of charge per second passing a certain point. I should say what is current, I suppose. As well, how would you represent what is current in this model, and how would you measure the current in this model? I'll give you 10 seconds. It's a bit of a sloppy question, and then I'll talk you through what I'm thinking. What is current in this model? So what I'm going to say is that current, it's kind of how many trucks are passing a certain point per second, isn't it? Really, like electrons carry charge, which is measured in coulombs. But yeah, how I would measure that current would be maybe just have a little person at the side of the road with a stopwatch writing down how many trucks go past every second, okay? Right, so if current, this is what I really want to get to, if current is the rate of flow of charge, can you tell me what the units of current are? Current is the rate of flow of charge. It's the charge passing a certain point per unit time. What's the unit of current? The coulomb is the unit of charge. But if current is how much charge passes a certain point per second, what's the unit of current? Man, with the tricksy questions. I'm going to write something on the board while you think about it. There we go. You had a think? And some of you going, don't know, just tell me. And some of you going, this is the answer. Right, charge is measured in coulombs, like the amount of positivity or negativity, the amount of electrons going by. Charge is measured in coulombs. Current is how much charge is going past per second. So the unit of current is the coulomb, is coulombs per second. And if you remember our speed, distance, time lessons where we talked about how speed is measured in meters per second, you might remember that coulombs per second, if coulombs, the symbol for coulomb is a capital C, and the symbol for a second is obviously S, you can write it like this, C per S, right? Just like meters per second for speed, coulombs per second for current. Except that's not what we do, because we're physicists. We're super lazy. So instead of saying coulombs per second, which you've probably never heard of, we actually measure it to be, we call coulombs per second amps. Yeah, I know. So when you're talking about how much current, you would say like 5 amps or 10 amps or 15 amps, just with an A. But I think it's useful for you to know that what amps actually are is coulombs per second. It'll make more sense, I think. It'll help you with these questions. All right then, just to be really annoying, if the units of current are coulombs per second, amps for short, we'll always say amps, but deep inside we know that amps means coulombs per second. If current is the amount of coulombs per second, what's the equation for currents? What is the equation for current? You knew I was going to ask that. Come on, you can do it. The unit for current is coulombs per second, amount of charge per second. So the equation for current, it kind of tells us, do you remember when we were doing our distance time lessons? Speed, this is what I always come back to. Speed equals distance divided by time, yeah? And the units for speed are meters, which measures distance, per second. You can kind of see it in the equation. It's meters per second, meters/second. So if you know that current is charge per second, you know that the equation for current is charge divided by time. Is that all right? Just going to keep banging on about this because I really, really think it helps with understanding when you're doing questions. Current, that is the equation for current. Anyway, the symbol for current, I have to tell you, but we won't go into it too much because I feel like I've massively confused you enough already. For reasons, the symbol for current is an I, the symbol for charge is a Q, obviously the symbol for time is a T, but don't worry about those yet. The units you're going to use are amps A, coulombs C, and seconds for time. I'm just going to give you the questions. I feel like this has already got wildly too confusing. Here we go. Have a go at these. I'll do them with you in the background and go through the answers. So current equals charge divided by time. I've rearranged it once for you. Charge equals current times time. You should really be able now to rearrange that equation to know what time equals. So have a go at these. They get harder. Question 1. 4 coulombs of charge passes through a lamp in 1 second. What is the current flowing? If you've got 4 coulombs of charge passing through a lamp in 1 second, what current is flowing? So you've got charge, you've got time, you just need to work out the current. Question 2. Calculators at the ready, by the way, please. There's no extra points for doing this in your head. 9,000 coulombs of charge pass through a circuit in 3,600 seconds. What current is flowing? 900 coulombs of charge passing through a circuit in 3,600 seconds. How much current is flowing? Number 3, this is true story. The longest lightning flash ever was 30,000 amps and carried a charge of 510,000 coulombs. How many seconds did it last? That answer is true. Question 4, how long will it take for a 12 amp current to transfer 2,520 coulombs of charge? Give your answer in minutes, because why not? And number 5, a light bulb with a current of 0.5 amps flowing through it is left on for 10 minutes. How much charge flows through the bulb in that time? Right, you lot probably nearly finished now, so I better get started. Okay, I'll go through the answers to the first two for you. Excuse me. So if you haven't got those, then you're probably struggling to do the rest. Okay, so number one, 4 coulombs of charge passes through a lamp in 1 second. What current is flowing? Well, you're looking for current, and you've got the charge and you've got the time. So you just plug it in, okay? Write down the equation. Always write down the equation. Current equals charge divided by time, which is 4 coulombs divided by 1 second. Can you give yourself some marks if you've actually written 4 coulombs divided by 1 second and not just 4 divided by 1? So I've put equals 4 coulombs per second because I can see now really easily, because I've done that my answer is in coulombs per second, because whatever you do to the numbers, you just do to the units. So C/S. And then I've put 4 coulombs per second equals 4 amps. Get used to doing that, please, instead of just, oh yeah, I'm looking for a current, so I'm just going to put an A on the end of my answer. Especially when you get further down the line and you might have done loads of different stages. It's so useful to be able to quickly see, oh, I know my answer's right because the units have worked out. And the second one is 9,000 coulombs divided by 3,600 seconds, which gives you 2.5 coulombs per second. Look, it does. And then I know that that's 2.5 amps. It's just a nice way of saying it. All right, carry on. So the answer to number 3. We're looking for, we've got current this time, 30,000 amps, and we've got coulombs, 510,000 of them. So we've got to rearrange our equation to try and find time, yeah? So time equals charge divided by current. Our charge is 510,000 coulombs. Our current is 30,000 amps, amps with a capital A, by the way. So it's 17 seconds. Can you believe that? It was only measured last year. A lightning bolt that lasted 17 seconds. Incredible. 17 seconds. Number 4. The answer I have to number 4 is we've got 12 amps, 2,520 coulombs of charge. Give your answer in minutes. So we're looking for time again. So I've done my charge divided by my current, which has given me an answer of 210 seconds. What is that in minutes? Well, there's 60 seconds in 1 minute. So you need to know how many times 210 seconds fits in to 60, don't you? So it's 210 divided by 60, which gives you 3.5 minutes. If you're not so good at this kind of thing and you can't see what to do, just make sure you really check your answer. Like if you accidentally did 210 times 60, then you'd get an answer in thousands. And obviously 210 seconds isn't going to be like thousands of minutes. So if you're not sure, then just keep checking and thinking about it. Right, last one. Did I manage to catch you out with number 5? Did you see that it's minutes, not seconds? Right, let's go through this last one then. Yeah, so a light bulb with a current of 0.5 amps flowing through it is left on for 10 minutes. How much charge flows through the bulb? Well, first of all, write down your equation. Charge equals current times time. Our current is 0.5 amps, and our time is 10 minutes. Why can't I just do 0.5 amps times 10 minutes to get an answer? Why not? Why? Go on, actually tell me, why can't I do that? This A is a problem, isn't it? What does this A mean? You got it? So because we know that amps actually means coulombs per second, then we'd be timesing seconds per minutes, wouldn't we? Seconds is sort of built into amps. So, and you can't time seconds by minutes. That is total nonsense. You've got to convert. So we got to convert the minutes into seconds. So there's 60 seconds in 1 minute. So I just need 60 lots of 10 to make 600 seconds, okay? And then you just do 0.5 amps times 600 seconds, which is 300 coulombs. Lovely. I wonder if you don't believe me, can we do what are we doing with the units here? We've got coulombs per second, and we're timesing that by seconds. Yeah, so can you see that if you've got something divided by something times the same thing, like 4 divided by 2 is 2, but times 2, you get it up to 4 again. So those seconds cancel out, and you're just left with the coulombs, which is the right answer. This is what you end up doing a lot with A-level questions, just to check you've got it right. Brilliant. Right, you lot. That is the end of our lesson on current electricity, except I've got to you just a few, they'll probably seem quite easy compared to that. Past paper questions, just multiple choice questions for you to do. If you would like to support me, if you are enjoying these lessons, if you are used to paying for lessons, then you can go to my About section of YouTube. It takes you to this website called Coffee, where I will send you nice things for supporting me. So enough people are supporting me with £5 a month that I can do this IGCSE lesson every week in term time, and a Lego Storytime show, and like an all ages home ed lesson, which is on the periodic table at the moment, if you fancy coming to that. And everyone who supports me with £5 a month gets sent some rainbow glasses. Since you're doing IGCSE, I will give them their proper name, diffraction glasses. Look, here's what you see if you look at a light through the rainbow glasses. How good is that? White light diffracting, so nice. And I'll send you a description of how they work, and I'll send you Theatre of Science magazine as well, because it's very good. I want you to have it. This is one of my favourite past issues. It's a bumper issue on colour. So it's got a beautiful comic in it about Monet and a superpower that he has, with some gorgeous Monet paintings that you can enjoy. It's got the truth about primary colours: red, yellow and blue, not the primary colours. Like, not even of paint, just not the primary colours. I know, I couldn't believe it either. So thank you everyone who has signed up to receive that. Much appreciated. Right, I'll do the past GCSE questions, and then I'll go to my Facebook page and see if anyone has written me any messages. Here we go. So just 3 for you, but they are proper past questions. A current of 20 amps is the same as, is it A, 20 amps per coulomb, B, 20 coulombs per second, or C, 20... Oh no! What happened? Orientation is locked. Okay, wait. No. Oh, it's okay. The smashing sound was my Lego phone holder falling to bits, not my iPhone falling to bits. and the screaming sound was just a yelp of despair, not pain. Okay, it's fine. It's almost like using a phone holder made of Lego balanced on top of business cards with the wrong email address on. Is not a goer, isn't it? Never mind. It's just... Sorry. I am gonna have to suck it up and buy a phone holder, aren't I? I've been really enjoying the fact that everything around me is made of Lego. Okay. A current of 20 amps is the same as what? Which symbol shows a battery? Is it a circle with the cross through it, a long line and then a short line cutting over a wire, 3 little dots with a line joining one of the dots, they're in a kind of triangle shape so that there's a gap in between them? Or is it D, a short line, a long line, a short line, and then a long line? And question 3, a bulb lights up. This proves A, a current is flowing, B, there is a cell connected, C, there is a battery connected, or D, the bulb is faulty. If you've already done that on your board, you can like, you can subscribe, or you can go to my Facebook page where I've put a post saying, if you would like to ask me any questions, ask them here. So I'm going to go there in a sec and see if any of you have said hello. Okay, 20 amps is the same as 20 coulombs per second. Well done if you got that. The symbol showing a battery, well, B shows a cell, a single thing that we have been calling a battery our entire lives, but D shows a battery, because there's more than one cell in a row. And if a bulb lights up, all it proves is that a current is flowing. There might be a cell connected and there might be a battery connected. But it could be attached to the mains, couldn't it? Like I've got a light bulb here which is lit up. There are no batteries connected to it. It's running on mains electricity, which we'll talk about later. The bulb could even be faulty and still lit up, but you could get an electric shock if you touch it. Just don't know. But if a bulb's lit up, then for sure electricity is flowing. Current is flowing. Right, let's go to my homepage and see if anyone said hello. If you have not said hello, then you are now free to go. Well, I don't know, someone might have asked a really interesting question, I suppose. So you might want to stick around and see if I answer it. Oh, not a single comment! Is that the truth? Wow, I don't think that's ever happened before. All right, cool. Then we can all just, well, say go home. We're probably already all at home. We can all do the opposite of going home. Go off and have fun times. I've just refreshed, like slightly optimistic thing. Oh, there are comments. See, it's always good to be optimistic. Oh, come on! Yes, Grace and Rose. Hello, Chloe. Just Grace. Sorry, Grace. Rose? I didn't mean you. Oh, what a brilliant question. Does a source of electricity ever run out of electrons? Does a source of electricity ever run out of electrons? What a brilliant question. I must admit, I'm a little bit rusty on how batteries work. Like, I just keep reading about it, and then the information just keeps plopping out of my brain. So I don't know if I can really answer that. I mean, yes, some sources of electricity definitely run out of electrons, but it's not so much running out of electrons as when electrons sort of like get to where they want to be, if you know what I mean. Like essentially a battery is kind of moving electrons around so that they're sort of more stable, I suppose. I'm just riffing. Grace, you can tell, can't you? I don't know. I'll look. Don't make me look up how a battery works again. Oh, you look it up. I don't know. It's just not on the syllabus, so I've been really lazy. I've just never looked at it. I will look at it a bit because I'm a bit embarrassed about how blah, 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 blah this answer was. Chloe, hello. Thank you for not asking any different questions. Thank you for watching, everyone. And there's plenty of other people here who are not commenting on Facebook. Maybe you don't have Facebook accounts. Good for you. Thank you so much for still being here and for watching, and I will see you next week where we will do voltage. See you soon. Bye.